Hi, this is Jihong Park, a lecturer at Deakin University in Australia. And today I'd like to share my ongoing work in collaboration with Yonsei University and the University of Oulu, which is about how to design communication efficient split learning. Here's the motivation. We are living in the era of machine learning plus X application. While pursuing machine learning plus X, we often encounter the lack of data samples at a single location. In other words, we should exchange data samples, but that is often restricted by some privacy issues and limited communication and computing resources. This motivates us to develop communication efficient and privacy preserving distributed learning frameworks. In this respect, many promising distributed learning frameworks have recently been proposed, and among them, in this talk, we focus on the communication efficiency of split learning as compared with a well-known framework, federated learning. So first, consider a parameter server communicating with multiple remotely located workers. Then, in federated learning, both uplink and downlink payloads are the entire model parameters, and the communication interval is periodic. On the other hand, in split learning, the uplink and downlink payloads are single layer activations and the gradients, respectively, and they are exchanged for each sample. In other words, federated learning can be regarded as a shower, while the split learning is many drops. The question is whether many drops exceeds a shower or not. Interestingly, the prior works by the host of this workshop have already shown that split learning can achieve higher accuracy and faster convergence with smaller payload sizes compared to federated learning. So in terms of the accumulated bit cost until training completion, split learning is more communication efficient than federated learning. However, if you go beyond counting bits, then things are different. For instance, what about the impact of stragglers and latency? Answering this question is not trivial, particularly under intermittent connectivity, such as wireless links that are essential in enabling large-scale split learning, but whose channel quality is time-varying. With this motivation, in this talk, we aim to ask and answer three key questions. Here's the first one. Can split learning control the number of stragglers? To begin with, let's recall the vanilla split learning operations. It is sequentially operated and is communicated per sample. For scalability, we consider its parallelized version, where at the worker side, data feeding is synchronous with respect to the label, and at the server side, concatenation is applied. Then the problem is that neural network architecture is not flexible, whereas communication channel quality fluctuates over time. Therefore, the server should always wait until the last straggler, whose worst case latency could become infinitely long. To fix this problem, we can add an average pooling layer aggregating all the uploaded activations, regardless of the number of uploads. Thereby, we can dynamically adjust the number of stragglers in split learning. There are several backgrounds on this. First, average pooled representations can be viewed as equally manifold mixed representation that are known to be trained as good as separate data samples. Second, based on another work to be presented as far as I remember tomorrow, we know that average pooling is effective in vertical partitioning with sample synchronous pooling. We can test the same idea for our horizontal partitioning with label synchronous pooling. And here's the result. The accuracy and convergence speed of average pooling is as good as that of concatenation as expected. In other words, pooling communication efficiency is a free lunch without compromising neither accuracy nor convergence. Next question, can split learning support periodic communication with low latency? In federated learning, workers communicate with the server at intervals of multiple local iterations. By contrast, in split learning, workers by default communicate with the server per every iteration. And fixing this issue is not a difficult problem. We can just simply increase the batch size. Here comes the background. The maximum communication data rate, which is known as channel capacity, is a well-known logarithmic function of signal-to-noise ratio. And this is achieved when the data packet length n goes to infinity. Otherwise, there exists a data rate loss term that diminishes with n. Here, the batch size increase corresponds to aggregating data packets, increasing n. Therefore, we can reduce the data rate loss when we increase the batch size. Consequently, we can observe the effectiveness of batch size increase in terms of latency, as shown in the yellow curve in the simulation figure on the left-hand side. In our simulation settings, accuracy decreases with the batch size, yielding an accuracy latency trade-off. And there are many techniques to improve accuracy under large batch sizes. So I expect one can even show a win-win strategy in the near future. Finally, the last question, can split learning handle and mitigate stragglers? To answer this question, let's suppose a straggler whose omnic transmission was failed. In split learning, this means that the weak connection between the straggling worker with the solver is dropped out. Therefore, the solver cannot even calculate the gradient for the straggler. A naive solution is perhaps to aggregate a non-straggling worker's gradients and enforce this average gradient to the straggler. Unfortunately, in our preliminary simulations, we observed that downloading average gradient by stragglers even decreases accuracy, particularly when the number of stragglers becomes large. To overcome such a fundamental limitation, we propose federated split distillation, in which gradient backpropagation is replaced with surface output propagation. Then, by running knowledge distillation locally at the worker side, workers can infuse the solver's knowledge into their models. In fact, this idea was inspired by local parallel training presented just before this talk. In local parallel training, each chunk of layers is associated with an auxiliary output layer to enable local training. Here, we can view the entire model as a teacher and one chunk as a student. Then knowledge distillation can update the student by comparing the outputs of the teacher and student. Applying this idea to split learning, the worker now has a student's output and the server has a teacher's output. Then in the forward direction, following local parallel training, both worker and server can locally update their layers. And in the backward direction, workers can download the server's output and update their local models by locally running knowledge distillation. Since this server's output always exists, even for stragglers, we can handle and mitigate stragglers. We tested this idea for a single worker with a split version of VG16 model, and we validate that such an output backpropagation improves the worker's accuracy. And based on this, we are currently extending this implementation to multiple worker cases. Here's the conclusion. To improve the communication efficiency of split learning, we need to co-design split learning model architectures and communication techniques. To mention a few, we can use average pooling, increase the batch size, and propagate global output rather than gradient. I believe that this new direction of research is still in very early stage, and we need more studies on energy footprints and privacy issues, as well as developing novel analytic tools to prove the convergence and the like. And I hope you enjoy this talk and you can come join us. Let me conclude this talk with an advertisement. Tomorrow morning, our collaborator, Yusuke Koda, will present our two wireless communication applications where we fuse RF signals and RGB camera image data through split learning. I look forward to seeing you all again tomorrow. Thank you.